Okay, this is a quick introduction to vapor phase reflow, and it's going to give you a little history on the way. If you have experience of vapor phase in the earlier stages of your career, typically that would indicate you've been in this industry for quite some period of time. Um, Vapor phase has its history way back 30 plus years ago, predates convection, predates infrared, and was covered under a patent that was issued to Robert Christian Fahl and Hans Hugo Arman, working for Western Electric and Bell Labs, who were developing mass soldering methodologies for what's obviously become a very common process, electronics assembly. They patented the system under methods for fusing, soldering, or brazing. Today, typically, the vapor phase process only covers soldering, but they were thinking ahead. These three illustrations are taken directly from the patent document, and the batch process you see as Fig 1 is actually very reminiscent of some machine designs that you'll still see today, where you have a tank. The tank has a fluid reservoir, and within the fluid reservoir you have heating elements. Those heating elements impart energy to the fluid. The fluid evaporates, and it is that vapor blanket that we're in essence utilizing for the transmission of heat. In the top side of the tank, you see under item 5, you have a series of cooling coils, and in the old days, those cooling coils were there to condense vapor that may be escaping through the top of the tank, and also to act as a mechanism for drawing some of the heat out of the circuit board, which had just previously been soldered. Inline machines today are very, very common. There's a direct equivalent to convection reflow systems. However, the mechanical layout, as you can imagine, is significantly different than that which is prescribed here. And lastly, vapor phase in combination with wave solder, whilst the vapor phase process has attributes which would be extremely beneficial to wave solder, I've never seen a system which utilized the two technologies in combination. So what is vapor phase? It's very simplistically the use of a vapor to transmit heat via condensation onto a circuit board and its components, and it would be analogous to cooking with steam. The difference being steam's maximum temperature under a non-pressurized ambient environment would be 100 degrees Celsius, and we're typically operating at temperatures in excess of 200, 210 degrees Celsius. The fluids available today actually allow us to work up to a max of 260 degrees Celsius. The basic premise, as is with the system of cooking, as the vapor changes state, i.e. it turns from a vapor back into a liquid, it goes through a latent thermal transfer mechanism, and its energy is imparted to the cooler object, and in this case we would be talking about the circuit board and its components. It's very important that you at least establish a connection between temperature transfer rates and energy. Temperature is a measurement of energy, and by controlling energy we are controlling the thermal transmission rate. So looking back, obviously vapor phase fell out of favor for any number of reasons, but many years ago. And in large part, this was due to its immense uncontrolled thermal capacity. You basically had systems which could provide and did provide too much energy. So too much energy, too much heat, very little control. You were experiencing extraordinary ramp rates, and ramp rates in excess of 10 degrees Celsius per second were common. They weren't uncommon, they were actually common. That resulted in any number of failure modes. Tombstoning would probably be the most well recognized, but more insidious would be circuit board failures, where the expansion of uncured chemistry within the circuit boards often led to delamination, which not necessarily could be found through test and would exhibit itself as field failure. They were typically batch oriented only. No inline systems existed at that stage, and last but not least, the chemistries were deemed inappropriate and ultimately deemed illegal under the Kyoto and Montreal Conventions simply because they were ozone depleters. But above and beyond that, under certain conditions they were extremely corrosive, they were very, very noxious, and created any number of maintenance issues for the machinery that they were actually being used within, and did present some health hazards to the operators. Well, what's changed? A significant amount has changed. The chemistry today is no longer solvent-based, it's actually polymer-based. The chemistries are extraordinarily stable. They are qualified as not being ozone depletive. They are qualified as being inert in terms of their operation, and are considered safe when talking to operator exposure. So the chemistry issue has been resolved. Thermal control systems have come a phenomenally long way, and we are no longer binary. We do have graduated control systems that allow us to manage the energy flow into the fluid, and consequentially, by managing energy flow into the fluid, we can now manage energy flow, i.e. temperature, into the circuit boards. Machine design has come a phenomenally long way, and today we enjoy batch systems, small, large, extraordinarily large, and inline systems catering to low, medium, and extremely high volume production environments. Cost of operation of a vapor phase system, it seems almost counterintuitive, but it's actually less expensive to run a vapor phase machine than it would be an equivalent convection reflow system. And the process demands, vapor phase is simply a better process for lead-free than convection. We are able to reflow in an oxygen-free environment, not oxygen-reduced, but free. And we're also able to manage peak temperature very, very precisely. And through the profile, we're able to bring all aspects of the assembly to the same temperature, so negating the issue of any delta T's. So real quickly, just to encapsulate most of what it is I've just covered, today we have a phenomenal thermal capacity in these machines, but we now have control architecture in place, so we are able to, one, zero the delta T's at peak temperature. We're able to provide pre-selection of peak temperature through the appropriate choice of the fluid boiling point. We're able to control ramp rates at anywhere from 1 to 4 degrees C per second typically. We are preheating and reflowing in an oxygen-free environment. Color, mass, density independence. Very sophisticated auto process protection, which allows us to protect against the mismatch of a given profile to a given circuit board. Peak temperature control means that we simply cannot overcook or over temp a circuit board. Machine designs are very, very flexible, very, very scalable. Process times are typically shorter as a result of not needing that saturation period in the reflow profile itself. And we offer the lowest potential for damage when considering all the current available soldering techniques, and we do have the ability to do true batch size 1, very, very advantageous for high reliability environments where you simply don't have the luxury of multiple panels and the sacrificing of one to profile a system to the betterment of the others. We can profile and we can reflow a single board with zero risk of damaging that product. So I hope you find this helpful. I'm going to be covering a few other aspects of vapor phase in some other clips.